you are not very, there are very few, so you could interrupt me, there's no problem. And I will start by talking about some historical events, I would say, in the audio and speech recognition that started in the 60s up until now with the vocal assistants that you might know as Alexa or Siri or the GPT new assistant. So let us first look at this video. It might start. So this is a video from the IBM archives in 1961. The video. Okay. So as you have seen, the audio recognition system were very old. So the first one, maybe, or the first memorable one was the IBM shoebox that permitted to recognize up to 16 commands, vocal commands, and performed arithmetic operations. So, and as you might have understood from previous presentation in this course, is that modern AI was invented like some years ago, and it could not be possible that this device was implemented using neural networks or AI. So there were things done in automatic speech recognition before, and we will see some of them before diving in the modern speech recognition system. Is it okay for you? Okay. So as a starting point, this is a question maybe for you and also for people on Zoom. What is a sound? For you, what is a sound? Yeah, please.
It's pressure. It's a pressure that reaches the ear.
It's a pressure that reaches the ear. Okay. Any other answer? What is the sound? No. So perhaps your colleague have said something that is close to the truth. The sound is a wave, and it could be a mechanical wave. And when it reaches our ears, there are an auditory system that process this wave. So a sound is a wave. And here, for example, in this image, you have a wave in blue on the top. And ultimately, what is sound? Sound is something that looks like this. It could be encoded as a 1D signal. And yeah, so it is sufficient to characterize any sound. It has some kind of periodicity sometimes. So, and this is common to all kind of intelligible sound, while the noise could be just a line, for example, white noise. And yeah, we will see that. So the sound is a wave. It's a signal, and actually it's a physical wave, so it is continuous. But then for our systems that work on quantized numbers, what we do is that we sample this wave. So we have something called a sample rate, and for every, for example, millisecond or less, we take 1 point of this wave. But you would say that maybe it could alter the quality of sound or the information, because ultimately you are not using all the information in the sound data, but only few points. Well, there is a theorem by Nyquist and Shannon that says actually that for a audio signal, to recover somehow all the information when sampling an audio signal, you should sample at a rate more than 2 times the maximum frequency of this rate. So for example, if you have a sound that has a frequency or a maximal frequency of 8 kilohertz, then it is sufficient to take a sampling rate at 16 kilohertz to recover all the information. And this is why, for example, in CDs or in audio that we use today, we use 44 kilohertz. So 44 kilohertz, it's because half of this is 22 kilohertz, and this corresponds to almost all what the humans could hear. So as a human, you could not hear frequencies more than 22 kilohertz. So this is why we are sampling our sound at 44, which is more than enough, because we know that humans are very limited. Sometimes even 10 kilohertz, they could not hear that. So, yeah. So once we have this audio signal, what we could do is to perform a transform on it. So usually what is used is a Fourier transform. Have you ever heard about Fourier transform or Fourier analysis? No. So Fourier transform is a transform that takes a signal and gives you another signal, and in another domain. So it takes a signal, for example, in time, and gives you a transform that is in frequency. And we can use this transform to our sound, and this gives us a spectrogram of the sound. And as you can see here on the slide, this is actually a transform of a sound, and you have in the x-axis the time axis, and then in the y-axis the frequency axis, and the colors here stand for the power of the signal. So the more the power is, the more the signal is powerful, the more you have like bright colors here. So this is a transform that we could have for our spectrogram. And ultimately, what Fourier transform tells us is how periodic the signal is. So we know how to transform the signal. And for example, if you take a transform of a constant, you have a certain function that is known in signal processing, but without entering too much into the details, what you should know of a Fourier transform, it's a tool that is very used in spectral analysis and for analyzing signals, and one of those signals is sound. Okay, so how now to encode audio? We have seen that you could encode that data point from the raw signal of audio, but also you could perform a Fourier transform on the signal and obtain a spectrogram out of this. Did you have a question? No? No? Okay. So here you have a pipeline on what is historically or what is traditionally done with the speech and with audio signals. So first, there is a pre-emphasis phase when you just higher the volume of you give actually more power to the signal. And then there is a phase of windowing. And what DFT means is the discrete Fourier transform. So it's a Fourier transform for discrete in discrete time. Sometimes what we use for speech is a special filter bank. So the one that we use is called the MEL filter bank. And I don't know if you heard about the MEL filter bank, but it is a filter bank that was done to mimic somehow the auditory system and of humans. So it's a filter bank that was done by neuroscientists to filter the sound, to give an approximation of the filtering of the sound as if it was heard by the humans. And then we could stop. So we could use the result of the filter bank. Sometimes we use the log of this the output of this filter bank, and we could use also the derivative of these signals. And actually, what are the MEL frequency cepstral coefficients? Those are coefficients associated with the derivatives of this signal, and this is called MFCC. So MFCC could be applied to have a filtering, to have first a discrete Fourier transform, then a filtering, then multiple coefficients corresponding to multiple derivatives of this signal. Okay, so as I said, the first option is to use maybe the audio as it is. So you use the raw signal. And a second option could be using the output of a MEL filter bank and also a discrete Fourier transform. So a raw signal, audio signal is 1D, while a signal that was transformed with Fourier transform is 2D. And what is something that you know that is 2D? How do we call an input that is 2D? Usually, it's an image. While so you see that audio could be transformed to an image. You have heard from past courses that there are a lot of literature, there are a lot of work done on how to process images. So you could obtain out of sound an image, and the image associated is called what I said before. What is the image that we get from audio? It's a spectrogram. Spectrogram, you apply the Fourier transform on the audio, it gives you a 2D signal that is called a spectrogram. Do you follow what I was saying? Okay, nice. Okay, so here is the point I said before. So raw signal, audio signal is usually sampled at 16K or 44K. And the reason is that we want to be beyond the frequency of Shannon to not have some loss of information. Okay. Okay, so option one is to use the raw audio signal and use it as a signal to train or to have a system, an audio recognition system. And as I said, the second option is to obtain the spectrogram out of this audio. So as I said, you could use filtering, special filtering, etc., MEL filtering, but you could also learn by neural networks those filtering. So there were work in 2021 that achieved that with learnable filter banks for to filter and also to compress the audio signal. So here is a spectrogram, a real spectrogram of a sentence. I will just play this sound. So this sentence could be transformed into the spectrogram that you just see here. So could you like comment somehow this spectrogram? What is so particular about this spectrogram? What do you notice? Like you, for example, what is your name? Yeah, so you see a regular patterns. So for example, there are some kind of periodicity along the frequency axis, and in fact, this is a characteristic. This is a signature of a human voice. So the vowels, for example, form this kind of particular patterns. There are also other remarks that we could see here. For example, yeah, you just next to her. Yeah, no, no. Yeah, Miss, please. What makes this image so particular? Something that is it like all black or is it all green? No. So what can you notice about this image? Sorry? So yeah, so there are sometimes frequencies that are more used than others, and actually the power is expressed by the color. So the more brightness you have, the more power. And as you can see, the signal is more bright in the range of yeah around between 10 and this corresponds actually to the human voice and also what we can hear. So it is normal that we will not have frequencies. I don't know if you are a very good singer, for example, you could reach high frequencies, etc. But the common human voice. So just by looking at the spectrogram, you could say that it is a human voice because you have something that is in the range of the actual frequency of what humans can produce and hear, and at the same time you see this characteristic forms of vowels in the spectrogram. Another remark, maybe you, sir.
But we can see that they're like divided in rectangles.
Exactly. So there are some rectangles that are like dark, and then there are rectangles. So this is an artifact of binning. So this is the sampling, etc. Normally it should be smooth, but this is an artifact. But we can notice that there is a huge rectangle that is dark, and then a huge, less huge rectangle that is dark at the end. And what do you think it corresponds to? Exactly. So when there is no sound, there is no power. So the spectrogram should be black. So just from this spectrogram, we could interpret a lot of things. Obviously, we cannot say restitute the sentence that was said because we are not trained as humans. Our eyes are not trained to recognize those patterns. But actually, what you can do is to train a model to recognize those patterns from the spectrogram. And as we will see in the lab after this presentation, this could be done. And actually, this is how it is done in practice nowadays to learn audio. So as I said, there were a lot of improvements in audio and speech recognition systems from the last century up until now. And as you can see, humanity has advanced a lot in this field. In the beginning, we were struggling to have just few words. Then in the 70s, 80s, we could have whole sentences, etc., of connected speech. So this is another difficulty that you could recognize single and isolated words, but then to recognize a whole text, you should have a knowledge of when the sentence end, when the word end, what is a vowel, what is a consonant, etc., what is the characters. This is hard, but actually nowadays we have systems that could transcript more or less the result of a whole speech. So, for example, the whole course I am saying, it could be transcribed, and then it will not be 100%, but it will be sufficient to understand and know what was said during this course, for example. Okay, so maybe one of the first models that was used before the artificial intelligence era, etc., was the Markov hidden model. So HMM, Markov hidden models. And actually, it is a probabilistic model that says, okay, the state of the model at state 1, for example, depends only on the past. So as you might have grasped, speech is causal. So for example, I do not speak about something that will happen in the future. So for example, all what I said is sequential. I do not have something in the past, in the future that could influence the past. Yeah, okay. So this is why we use Markov model. When you hear Markov chains, for example, it means that is a system that relies on the past. And there is a chain that relies on the past. I'm not going to enter into the details of Markovian theory, but this is good for your vocabulary. And yeah, so for isolated words, what was used are those models. So those models rely on the past states of the system, but also they could rely on the current states. This is why you have some loops, inner loops for the state. And then they produce outputs. So B1, B2, B3, etc. produce outputs. As for example, here, the word for could be represented by a Markov model, hidden model, and every phoneme could be characterized by a state. So the F could be characterized by state 1, and then AO, so the sound O, could be characterized by another state. So those were trained using the maximization of probability. And what was used here is the bias law. So you know that your vocabulary is composed of those, for example, 4 words. So let's say our vocabulary has the word up, down, left, and right. And the task is to classify if the feature that was said was up or down or left or right. So you could calculate the probability that the acoustic feature O with respect to up, what is it? And then for down, to calculate the probability of O knowing that it was the word down that was said, etc., and compute those probabilities and take the maximum probability of this. And this will be likely the word that was said. So I don't know if I should go into the details of the equations, but what ultimately is the maximization of probability that we were using? It is this one. So we should find the argmax of the probability of the word W, knowing the speech sequence X. So we could use the bias law to compute the probability of X knowing W times the probability of W. And then we could use we could compose those probabilities with, for example, other things. So, for example, you could use a lexicon, which is a lexicon is does give you the matching between the word and what is probable in the vocabulary. So, for example, it is very rare to find some words next to each other, and very likely to find some words with another. So, for example, if I say the president of the Republic of France, the word president and the Republic of France is likely to occur, but the president of Apples, it is not that. And this information is somehow given by the lexicon, by the language model, and the language model is could back in the 70s, the language models were not like those we are using today. We used something called n-grams, so we knew the probability of some words with respect to their position. So up to 8 grams, for example, we know if this sentence is probable, but then more, we did not have that. But today, you all know a language model. So for example, I don't know, a language model that you know. GPT. So GPT is a language model that was more capable of doing this kind of things than the language model in Ngram that were like done sometimes by human beings that compiled the vocabulary, etc., the dictionaries, etc., of how probable was a word with respect to the other. Okay, so as you can see in the 70s, 80s, to make a model of audio and speech recognition, you had first to have a model, acoustic model for phones. So this was done by hidden Markov models. And then you would have a language model and a pronunciation models that were very costly to have. So those were crafted by hand, or there was some algorithms that were used, like for example, n-grams, back-off strategies, etc. There were some algorithms like Bomb Welsh, etc., Viterbi that were used. A really huge barrier for non-experts in the field. So to create a audio, you needed information about the fonts, about the pronunciation, about the language model, and all those were like jobs. People did have a job which was to create a model, a language model, etc. But with the advent of neural networks, we could try from end to end the automatic speech recognition system. So here, starting from the 2010, we could train a model using only the acoustic feature. We just give the model the acoustic feature, and we let the model train on data sets, huge data sets, and at the end, output a word sequence or a text sequence, etc. And this is what we are going to see now. So the question now is, how much are we done? Is the problem solved nowadays of audio and speech recognition? So according to big companies like Microsoft and Amazon, it is a solved problem, because now we have systems that are almost reliable at 95% or 99% for a long range of speech. We could, like for example, in YouTube, when you see a video of 2 hours, the transcript is almost perfect. But there are still a lot of things to do. So those concern mainly the English language. So we have a lot of resources for languages like English or European languages, and very few for local languages, or other languages, although there are a lot of speakers of those languages. So for example, I don't know, in Indian languages, etc. There are a lot of speakers of those languages, but still the systems are not that well established with respect to English. And the question now is, could we transfer somehow all those resources of English, etc., to other languages? Also, there are problems of regional accents. You have noticed that my English is not perfect British English or American English, and also your own accent of English is not the same as the one that was used for training the models. Also, sometimes you could switch the language. So, for example, you talk in French and then you say a word in English, and this is a particularly hard task for audio and speech recognition. Also, there are some questions on how to build fastly. So those systems were built, like for example, Amazon Alexa or Microsoft Siri, no, Siri is not Microsoft, it's Apple Siri, etc., were built using a lot of resources, a lot of text, a lot of audio recordings, etc. And the question is how to do the same but with less resources. And finally, sometimes in an controlled environment, when you have only one speaker, as I do now, it is easy to have the transcript of the conversation. But if you have multiple speakers, for example, or a crowd, there is noise, there is multiple persons interrupting each other, etc. The questions of who said what, when, etc. is more difficult than just transcripting audio. So there are many other things that could be done in this field. Okay, so now let us advance to some basic neural networks that could be used to extract speech or sound. So the first one is maybe that I will introduce are convolutional neural networks. Perhaps you have already had a course where those were explained, and actually convolutional neural networks were applied for images, and you have seen maybe a data set like okay, what was the data set? Were the images of what?
Various objects.
Of objects, etc. So maybe you have seen Cypher 10, and also the one with the numbers.
Yes.
It is called NIST. So okay, but those the convolutional neural networks were adapted for images. You could do convolutions in 1D. This perfectly works, but still we can perform it on the spectrogram. So a spectrogram is a 2D image, and you could feed it to your convolutional neural network as if it was an image, and then you let the neural network train, and it will recognize to associate, for example, this particular spectrogram corresponding to this particular sound to a label, which is, for example, a word or something. And this is what we are going to do during our lab. So maybe one of the first models that were used in this field for convolutional neural networks was VGG, but there are a lot. VGG is very old. Now you have more advanced neural networks, convolutional neural networks that we could apply. There were, like, for example, ResNet, and then other models, MobileNet, etc., etc. But all those, there are just like an improvement that was built on convolutional neural network. It's still a convolutional neural network, but it is more performance in terms of accuracy and in terms of throughput, etc. So when you pre-train a VGG, you have inputs that maximize the activation that looks like this. And as you can see, the neural network has learned at the end of training some patterns, and also has learned some input features that maximizes the activation. I will skip this. Okay, so for now, for feature extraction, so convolutional neural networks are reputable, are very known for feature extraction. You give them an input, it extracts the most relevant feature for your task. And this is a task that even humans could struggle with. So for example, as your human eye was not trained on recognizing the spectrogram, you could not recognize on the spectrogram what was said, while a convolutional neural network could. But this is good for short excerpts. So for example, a sentence of 2 or 3 words, etc., or just one word, and this works perfectly, and we are going to try it today in our lab. However, as I said, speech is causal, and speech might be long, and sometimes you could say something that has a relationship with something that was said way before in the past. So you need a certain notion of time in your system. Convolutional neural networks are great for something, inputs that are not temporal, while speech is intrinsically temporal. You just say something that relies on the past, but not something that will rely on future. And a great kind of neural networks that were introduced to have this notion of time were recurrent neural networks. And I believe also you have had a course or recurrent on recurrent neural network. So what are recurrent neural networks? They are neural networks that look like feed-forward neural networks, but then they have this sequentiality. So you have a hidden neuron H0, for example, that is dependent, let's say H2 that is dependent from H1 and H0. So you have neurons in time. It's not just neurons, but neurons with a time step. And then those neurons are fed with a sequence. So X here is a sequence, X0, X1, X2, etc. And they give outputs, Y0, Y1, etc. And this is particularly suitable for speech, because speech, as you might see, the sequence could be the sequence of words, and it gives you a sequence of words. You give the system a sequence of spoken words, X, and it gives you a sequence of written words, Y. And you could do that also at the letter level. So you give the system a sequence of speech X, and it gives you the sequence of letters. But however, what is done, it's at the lower levels that there are sequences that are produced that are corresponding to the phonemes that are said by the human being. And then other layers of the neural networks try to combine, to aggregate, to separate, etc., to obtain words, to obtain first to separate, to obtain letters, and then to aggregate, to obtain words, and then to obtain sentences, paragraphs, etc., and then you obtain the whole speech. So recurrent neural networks are great for that. One of the most known, I think, recurrent neural network that you might have seen is are LSTMs, long short-term memory neural networks. There are also GRUs, gated recurrent units, etc. I don't know if you have seen all the details, but as ResNet, MobileNet, etc., those are categories of convolutional neural networks. And in recurrent neural networks, you have categories like, for example, gated recurrent unit, etc., LSTM, etc. Great. I will skip this to talk about this. So maybe you have heard also about the revolution that transformers brought. So actually, transformers are a new kind of models that were introduced in 2017, and that show better performance than recurrent neural networks and also convolutions. And at the heart of transformers is the multi-head attention module. So the multi-head attention module, now with the hindsight, we can say that it is a kind of parallelization of what a recurrent neural network did. And actually, what this module brings is this layer. So here, the softmax of Q times K, actually it's K transpose times V. Those are matrix multiplication. And actually, this operation is called attention. And this is the operation that somehow parallelizes what a recurrent neural network did. And it is particularly suitable for training very large networks on a lot of data. And actually, the T in GPT, for example, is the transformer. So it's a generative pre-trained transformer. And at the heart of every GPT, there is something that looks like this for the moment. And yeah, so those transformers could be used in the speech field as well. So you could use a vision transformer and give it the spectrogram. So this is what was done in this work. Yeah, so you might say that there is no sequence in an image. So a certain way to create a sequence of an image is to take patches of the images. So to take the image, you just divide it into I don't know, 8 patches, and you feed sequentially this image to your transformer, or you could use a 1D transformer, as I said before, on the raw signal data. Yeah, so as I said, it was introduced in 2017, and actually the transformer has a multi-head attention layer that computes this operation Q times K times V with a softmax, etc. But what really is people don't say when they say this is that the majority of the work is done by the feed-forward network you see. After the feed-forward network, it's just a linear network. It's just an MLP, multi-layer perceptron. And actually, a lot of the work is done with this MLP, along with the multi-head attention, but still for non-sequential data, multi-head attention is not performing that good, but for very sequential data, attention is very important. So for example, for speech, for natural language processing, etc., the multi-head attention is very important, while in the computer vision, etc., images, etc., it is not that important. Okay. Okay, so as I said, transformers nowadays have taken over, took over major AI applications. What was used before were convolutions along with recurrent neural networks. But now more and more we see that transformers are taking over those models, and actually what works best is an hybridation of a lot of models. So you could have some convolution in the beginning to extract the suitable features and then give them to a transformer. To have a transformer is great for sequentiality, etc., for sequential data. So this is what works the most nowadays. So in conclusion, you have seen that automatic spatial cognition is a very dynamic research area, and as all areas in related to artificial intelligence, it takes a lot of knowledge from other fields like natural language processing or computer vision, and tries to adapt them to the audio and speech processing. There is a lot of things to say about how the human brain processes audio, etc. This is just an artificial way to treat these audio signals, while we know in the brain it is completely different. It is not, you don't have a transformer in your brain, although some of your neurons are capable of attention, etc., for making convolutions, etc. And yeah, it is still an active research area, and you could be a part of it in the future if you want. Thank you for your attention. We will now move to the practical work. And I invite you to take, to go to the page of the course and to open the notebook. Yeah, you could have uploaded me as well, but yeah, and for the people on Zoom, I invite you to do the same. Okay, so in this practical work, we will see how to classify audio commands. So we are going to use a small data set for our lab that was made by Google in 2017, I guess. And this data set has utterances of words, spoken words by many individuals. Those words there are 35 words. So there are commands, 0, 1, back, backward, I don't know. We will see them. Yeah, so I invite you to read the first cell. Yeah. Everyone has page. Yeah. So, are you familiar with PyTorch? No. I used in the previous course. Well, this is the final course, so maybe you have gathered a lot of experience from your past courses, and now you are fully proficient in PyTorch. But could you just tell me what does the line import torch? What does it do? The torch library, okay. And what is the torch.nn? Okay, so it is a package within the torch library that is called neural network. And then inside you have a module that is called functional. And actually, when you put in Python, this is Python, not PyTorch, as is just an alias for, instead of writing torch.nn, you write just nn. Okay, and then you have torch.optim. So this is a package within Torch for optimizers, and you might know one of them. Starts with an A. Adam, for example, no. SGD, no, never told you about that. Okay, so an optimizer is something that's optimized, obviously, but what it does actually, it performs the gradient descent for you. So you give it the model and the gradient, and actually what it does, it computes W, it receives W minus the gradient, and this is gradient distance. So, but it depending on the optimizer. So for example, SGD does that. So you give it weights, and it does it replaces the weight at the step S by the weight minus the gradient of the weight time the learning rate, and this is known as the gradient descent algorithm. And actually, it is what is used to train neural networks. So neural networks are great, but if you don't find the suitable weights in every neuron, then there is no training. So one way to train the neural network is to use gradient descent, and it minimizes the loss function using steps that are informed by the gradient. So we calculate the gradient. What is the gradient? No. What is the derivative? You see what a derivative is? Exactly, so it's fine slope. The gradient is the same operation, but in higher dimension. So instead of having a function of x, like for example, x squared, what is the derivative of x squared? No? 2x, yeah. But then this is the derivative in one dimension. If you have a function that has an output in a bigger dimension, it is not called the derivative anymore. It is called the gradient. And actually, x squared has a shape of like this. And then if you want to find the minimum of x squared, one way to do is to compute the gradient, which is 2x, and to say, well, the minimum, the extremum is at 2x equals 0. And you find 0. And actually, it has a minimum at 0. But in a very higher dimensional problem, this is not possible. So one way to do is to compute the gradient and to follow the gradient. I will show you maybe a gradient descent. So on Zoom, you could see what a gradient descent is. So what I said before was that, for example, this is a function that looks like x squared. And what does the gradient descent do is to find the minimum by doing those steps, and those steps are informed with the gradient. So maybe you could look at the image on Zoom, and finally you find the minimum. And actually, you could say that it is dumb to do like this because you do it in many steps. First step, then second step, etc., etc. We could have done it in one step. But the problem is that this function is very smooth, and the actual function in learning looks more like this. And the risk, if you do a big step, is to be stuck in, is to find another minimum. So the minimum here in this image is the one in blue. But if you take very small steps, it means that you are converging slower, and this could lead to being stuck in local minimum. While if you use bigger steps, you could never find it because you skip it each time, etc., etc. So all the AI, the task in AI is to find the suitable strategy to optimize the function, and sometimes it is very hard because those are simplistic examples, but the real problem is high dimensional because you have a lot of neurons, a lot of inputs, etc. And it scales, and the curse of dimensionality makes it very hard to find the global minimum of the problem directly. So this is why we are using optimizers, and some of them are XGD or Adam that uses momentum and makes the optimization better. Okay, so I am happy that I have said that to you, even if it was not on the scope of this course, but it is great to know this. And then you have Torch Audio. Torch Audio is a library built on Torch for audio, and Torch Vision as well for vision. We are not going to use Torch Vision. We are using Torch Audio. Sys is for the system functions. This is Python. Matplotlib is for plotting, etc. IPD is just for audio to hear audio. I'm going to hear audio. TQDM is for just you will see it's just for some nice plotting of progress bars, etc. Okay, and what I invite you to do is to execute your code on GPU. So we are going to use a GPU provided by who? Since we are on Colab. Colab is
from Google.
From Google. So those are GPUs somewhere in Google's clusters, and yeah, so we are going to use them. So here in execution, you should modify the type of execution from CPU to T4 GPUs. And let's hope there are enough of them for today. Okay, and then the second cell is to define the device. So the device here, we are going to use NVIDIA GPUs, and NVIDIA uses a language that is called CUDA. So those are named CUDA. Yeah, so do you know how to execute cells? Okay, Shift Enter, execute cells. Okay, let me execute those cells. So now you understand somehow what is happening. It's more clear than just having a bunch of imports and I don't know to what they are corresponding. Okay, then we are going to define a data set. So the data set, as I said, is called speech commands, and it is a data set of 35. It has a lot of excerpts, but the task is to classify correctly those audio excerpts according to a 35 labels that we are going to see. So here in this cell, what we are going to do is to download the dataset. So go ahead. You download the dataset, and yeah. Okay. And as you can see, it is 2.26 gigabytes of memory, which is good. And we are going to split the data set into a training set and a test set. Usually, sometimes they give you what is the training set and what is the test set. Sometimes not. And what you do in a classical classification task is to split as 80%, 20%, etc. To perform also cross-validation, etc. But yeah, and yeah, sometimes there is the validation set and the testing set. Did you hear about that? So the test set is really to test, and usually it is not shared with the people. It is something that is hidden to really assess if your model trained. And the validation set is accessible for you. The training set you train with this data, and the validation set, you could try your model on it, modify it, etc. A bad thing to do is to add the validation to the train. It is not usually permitted, and the test set should be hidden from the participants or from the people that designed the model. And here, just we are going to use a train set and a test set. And this test set is not hidden; it's just a validation set. But we are not going to do that very formal thing. And then I invite you to execute the following cell. And in this cell, we use PLT. What is PLT? It's an alias for plot of matplotlib. And the PLT is an alias of matplotlib.pyplot. And pyplot has a function called plot that plots images or plots data. And it does not plot images, it plots curves, graphics. And then here we plot what? We plot waveform. What is a waveform? Maybe in line 52, just before, we have said that train set 0, waveform, sample rate, label, etc. equal train set 0. What does this mean? Line 52. Who could explain line 52?
You're getting the data from the first item in the training set.
First item in the train set, which is item 0, and the data are?
The waveform, the sample rate.
So it is a tuple of 5, 1, 2, 3, 4, 5 things. The first one is the waveform, the second one is the sample rate, the third one is the labels, speaker ID, and utterance number. So the waveform is the actual sound, is the waveform. The sample rate is a number that says, okay, this sound was sampled at 16 hertz or 16K hertz. Label is the label of what was said. So if the word was 0, then the label should be 0. The speaker, there are many speakers, but we are not going to I'm not interested by the speaker here. We should just classify if the word that have been said was this one or not, and then a utterance number, because each speaker said the same word multiple times, just to have a diversity in our data set. So what we are going to focus on the waveform and the label. So, and we are going to try to match the waveform with the label. So here you can see the label at the next cell, and as you can see, it corresponds to a waveform of a sound. What are the characteristics of this plot? As we said before, there are
waves.
Yeah, it's a wave, and
begins in silence.
It begins in silence. It ends also in silence, and then in between you have something that is being said, and it is more or less periodical. Okay, and the sampling rate here is 16K. So we could, in the next cell, look at the labels. So I go ahead, and in this, it might take a lot of time because it is going through all the data set and gathering all the labels, and then it gives you a list of unique labels in the data set. This is done just to see how many labels are there. We know that there are 35, but just to check if there is not more or less labels. Okay. Do you have any questions so far? Great. And maybe it has almost finished. Yeah. We have the list of the words that we might encounter in this data set, and those were sorted by alphabetical order. And as you can see, the first word is backward, and the last word is 0. And the task is to find from the words that are spoken which one was said. Is it backward, 0, 1? Word for word, bird, cat. Okay. Okay, so we could also hear the sound that we have in our data set. So I invite you to run the next cell and to tell me what it does. What was the word?
Backward.
Backward. And could you comment on the code that was written here? What are we doing in the first line, for example? This first. Yeah, this don't do training. It's just we take the first word, the data set, we take the waveform of this word, and then the other information, so we don't care about them, so we put a star dash. And then what was the first word said? I don't think so, because there is another line after.
Yeah.
It is the second, so maybe backward is the second word.
Yeah, it should be.
Yeah. 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 Backward is the second word. If we try to erase those lines, now comment them. But yeah, you could change the number of points to hear other words if you want. Okay, so the second word in the data set was backward, the first one was back. And then maybe in the next cell we could hear the last word of the data set. And please tell me what is this word? It's 0. Okay. Okay, so those are raw data. Now what we are going to do is to format this data. So the first thing we are going to do is to resample the data. What is resampling? What is sampling?
From a population thinking from the
From a signal?
Yeah.
At fixed positions, taking a sub-signal. In French, we say sous-échantillon. It's a sample, a sub-sample. Okay, and what is resample? We change the sampling rate. So from 16K, we could change to 8K. And how are we going to do that? Yeah, but if you have a signal at 16K and you want to a sub-signal of 8,000.
We jump one.
Yeah, you should take one of two. And this is sufficient. And this is what is done by the function torch.audio.resample. Actually, you could do resample by lowering the sampling rate. It is hard to do in the other way because you need more information, but you could do it with interpolation. It does not work a lot. Do it. Okay. And why are we going to reduce the sample rate? What could be an advantage of doing that?
I think the model is faster.
Why?
There's less information.
There's less points, and actually, human beings need a high sampling rate, but machines, they could 8,000 could be sufficient for them. So we are going to use less sampling rate to have less information because it is a little bit overkilling the model. Okay, we could do that. We could stay with 16K. Usually in AI, people use 8K or 16K is very sufficient for all kind of tasks. Okay. Then what we are going to do is to obtain the spectrogram out of this sound. So in the next cell, we are going to use torch audio that transforms that MEL spectrogram. So this function does the job for you. So it does the Fourier transform and then the MEL filtering, etc. There are parameters, etc. to parameter this function. So go ahead, execute this line, and you obtain an image. Obviously, we are going to resize the image. Why? Okay, but we are going to resize in time and in frequency. So I might agree with you that we don't need all the frequencies, but are we going to need all the time? Because if you resize too short, maybe you could miss information. So we know in this dataset that the longest extract is like 1.5 seconds, I guess. So we could resize everyone to 1.5 or 1 second. But actually, there is another reason why we resize everyone to 1 second or to 1 second by, I don't know, 40 by 80. Do you see what is this reason? It's a technical reason. Actually, to train our model, we need batches of information. So batches are tensors. What is a tensor? Tensor is a matrix in a higher dimension. What is a matrix? It's a vector in 2D. What is a vector? A sequence of data. So if you have a vector of 5, and then you want a matrix, you could have a matrix of 5 by 10, and then a tensor, you could have a tensor of 5 by 10 by 7, etc. 5 by 10, it's a multi-dimensional vector. Okay, so we need those tensors. The problem is that if you have a data that is 8 by 10, and then another one that is 9 by 7, you could not concatenate them. So this is why you need your information to be in a tensor in order to be trained. And this is because we are training on GPU and on PyTorch, and PyTorch uses tensors. Everything in PyTorch is a tensor. So you need to construct the tensor from your data. So usually what is done here is to take the data and to play with it, to format the data to have tensors. And this is usually what we call data pre-processing. And the data scientists, the first step a data scientist does is this one. They look at the data, they try to figure out what are the labels, what is the data set, what is the data we have, and then they try to format it in a way that the models will work with it. So here you are doing the first step of every data scientist's job, which is the data, actually. And it is the most important because the models, they are already developed by other people. We already have ResNet, we already have pre-trained transformers, etc. So for someone that does data science, the most important thing is how to adapt the data to the models he is going to use. Okay, so let us look at the spectrogram. So here we show the spectrogram for the first data point in our train set, which was backward or back. And as you can see, it shows like this. So this is a spectrogram of a resampled signal, and that was resized to 40 by 80. You could change, for example, the number here in the train set to show another spectrogram. For example, for the fifth, etc. Okay, so those images we are going to use for our model, and we are going to use 2D spectrograms in this course, and maybe we could use at home another model with the raw data, etc. Okay, so let us execute the next cell. The next cell introduced two functions, like label to index and index to label. This is done. So yeah, I might ask you, why are we going to do that? So the labels are words. So backward, yes, etc. till 0, but we are going to transform them to 0, 1, 2, 3, 4, 5, etc. Why? Exactly. Neural network does not know sentences. It processes only numbers. Actually, to compute the loss function, you need the numbers with numbers. So we are going to say that back is 0 and backward is 1 and up to no, back is 0, backward is 1, and 0 is, the word 0 is 34, for example. Okay, so let's do that. We are going to create two functions, or we are going to need the function label to index to do that. And then our network will output an index. So it will say this utterance, this spoken word was index 0. And we will not know which one was 0. So we need another function, which is the inverse function, that takes 0 and gives you the corresponding label, which was back. Okay. So let us do that. Okay, and then we define a few things for our model. First, the data loader, so the train loader and the test loaders. And as I said before, the train loader takes the data and put them into batches. So for example, if you have a 40 by 80 spectrogram, it constructs you a tensor of batch size 40 by 80, and the batch size could be fixed. Here we fix it to 128 because each time we do a gradient descent, we are not using all the data set. We use a batch from the data set that was taken randomly of size 128, and then we use another one and another one, and every time we use a batch, this is called a gradient step. Each time we are doing step, and this is called a stochastic gradient descent. So gradient descent is when you use all the data at once each time. Here we are going to use few batches, fewer data points per batch, and then do it stochastically. And actually what we show is that actually it's done because we cannot process all the data at once. Or you should have a very large GPU or many GPUs and you parallelize everything on those GPUs. And actually, there are like mathematical proof that shows that the stochastic gradient descent algorithm converges. So you should not have all the data all the time. Sometimes you need only a stochastic information, which is a randomly chosen batch that gives you a direction. You follow this direction, then you choose another one, and somehow this is better than taking the whole data set. So we are going to use that. Let's, okay. I did not compile this one. Did not run this one, sorry. I'm not compiling anything. Okay. Do you have any question about this cell? Because I did not explain it very well. Okay, so now we are going to define a model, and we are going to use a convolutional neural network with convolution. So I have defined a model that is called conv model, and I invite you now to work a little bit and to complete the forward pass of the model. So here, the to-do part, here you should complete, and you have instructions in each step. So what we want to do, I have defined already the layers that you are going to use. You are going to use a first convolution, followed by pooling, followed by review. A convolution followed by review, followed by max pooling, and then another convolution, and then the same thing, etc. And at the end, you are going to apply two linear functions with reduce. So you have to work now a little bit. Yeah, and people on Zoom, you have to work as well. So I have put the dimensionality of the spectrogram at the beginning. So what is the dimensionality of the spectrogram? It is written. What is the dimension of the tensor in the input? 40 by 80, but then you have a batch of this. So it's 128 the size of the batch by 40 by 80. And sometimes for images, you have three colors, RGB. And so you have three channels. So you have 128, 3, 40 by 80. Here you don't have that. You have only one channel. And you have 128 by 1 by 40 by 80. So it's a 4D tensor of size 128 by 1 by 40 by 80. Actually, one could be removed and it's just a 3D tensor. Okay, so the first task is to apply the first layer of convolution, then the radio activation function, and then the max pooling. So go ahead, and if you are struggling with that, feel free to ask me. There was another person in Zoom who left, right? No? So there is only one person that is attending. Because Matthias is you. Okay. And Maureen Verdier is the only one that is here. So Maureen, please go ahead and complete the forward pass in this cell. If you are following, if you don't, then forget what I said. How many people were there here in the first session? 10? I just need an approximation, not 6 here and okay. Ah, they are abroad, okay. I will help you. You have never done that before in the previous classes? Okay. Just 1 minute and then okay, so how to apply a convolutional neural layer that was already defined. So here before, the first line here, line number 2, you have class conv model and between parentheses nm.module. What does that mean? It means that you are defining a new class that is called conv model, and it inherits from the class nm.module. And the nm.module is the generic class for the modules in PyTorch. So it will inherit a lot of good things, and one of them is the forward function that you are going to override. And the forward function actually computes the actual computation you want to do. So in forward. And there is something that is really cool in PyTorch, which is called automatic gradient, how do you call it? Automatic differentiation. So it calculates the gradients of a function for you. For example, if you give it the function x squared, it will compute the gradient for you, which is 2x and not x. And you can be sure that PyTorch will compute the exact gradient, and actually does it for very high dimensional functions. So you just give it the forward and it computes the backward, which is a revolution, by the way. Before, people computed the gradients by hand. So for example, me, for my first project in deep learning, I had to compute the gradients by hand with the mathematical formula, etc. But then what it does is it says that, okay, people usually use matrix multiplication, convolution, which could be written in somehow in a matrix computation. So I am going to provide the derivative of matrix multiplication. And then every time someone uses it, it will compute automatically this operation, but it does not solve the problem of stacking many matrix multiplication. So here we use a mathematical rule called the chain rule, and actually what the automatic differentiation package does is that it applies this chain rule. So the chain rule is the derivative of f composed with j. What is the derivative of f composed with j? F rangé, la dérivée de f rangé, c'est f' de g fois g'. And in fact, if you have f rangé, rang h, f composed with j, with h, etc., you could apply many times, and actually it is what this software does. So why is it useful? Because in neural network, you use the first convolution, which is f, and then the second convolution, which is j, and then the second, etc. And it's a composition of many functions. And you just have to write this composition. So in the forward, you just write f rangé, rang h, etc. And it computes the gradients for you automatically. So now the first function, which is f, is convolution. And I have defined it in self.conv1. So self.conv1 is an attribute, conv1. And I define it as nm.conv2d with n inputs, n channels, kernel size of 3, padding, etc. I am not entering into details of convolution. Normally you have seen that. So to apply this, what you could use is this. So I'm going to use self.conv1 that we have defined before, and you apply it on x. So if you do that, it will make the actual computation, but you have to save it somewhere. And how do we save the results of the output of a function? We create a variable. So we could say y is equal this. But do we need really to create a new variable? Because we are going to apply f composed with j, composed with h, etc. So we could put it in the same variable x. Okay. And then I asked you to apply the ReLU function. What is ReLU function? What is ReLU function? No, never heard before. What is an activation function? No. Sigmoid, no. ReLU. What is sigmoid?
Sigmoid is a curve.
Yeah, so it's a S-shaped function. And the ReLU also, no, it's not S-shaped. ReLU is max of 0 and x. So it is equal to 0 for negatives, and then it is equal to the identity for positive. And it is a kind of activation that we use in artificial neural networks. You could use sigmoid, but here I want you to use ReLU, which stands for rectified linear units. But actually what it does, I will show you a ReLU here in Zoom. It's this function. It's the maximum of 0 and x. And why are we going to use an activation function? What is the purpose of this activation? We have already used the convolution. Is it enough? No, it's not enough. Why? Actually, what we are trying to do is to construct a model that could approximate the function that takes an audio spectrogram and gives you a label. And this is a high dimensional function, and we should approximate it with our neural network. So we know that convolution is a linear operation. And actually, this operation is not linear. The function we want to approximate is not linear. So you should introduce somehow a non-linearity. Convolution is linear, but ReLU is not. Sigmoid is not. And those functions are used to give the neural network more expressive power. So a simple convolution could model every linear function, but not the non-linear function. Actually, we have a very powerful theorem on neural networks that say every continuous function could be approximated by a neural network of at least 2 layers. So if you have first layer, then activation, then second layer, the activation, it is sufficient to approximate any function you want. So this is a very powerful thing. And now we want to use a linear layer, which is convolution, followed by a ReLU function, which is non-linear. So how are we going to do this? We are going to use PyTorch. It has already implemented the max of 0 and x, and it is available in, I don't remember, you tell me, no, you don't know as well. So every time I don't remember something, the reflex is that I search for it in the documentation or in Google. So I just ask ReLU torch. And this is what you should have done also. And it says, okay, ReLU is in torch.nn.ReLU, and you could use it here, or you could use it as functional. So ReLU, like this is a module. So you could have done this as a module and say, okay, I'm going to define ReLU here and say that my activation is self.act and say it's torch. And actually I have an alias that's nn and say it's ReLU. Actually, the Colab editor helps you because it completes the function. It has auto completion. So you have ReLU here. And you are going to use it as an activation layer. So self.act. Oh, no. Do you have any question about this? So actually ReLU is just a fancy name to say we have done a function max of 0 and x. Every negative every negative x is going to 0, and then the positive part is staying the same. The positive elements are staying the same. I could have done that differently. So I could have asked f dot ReLU as well without defining this. This is the functional module of PyTorch. And then you should apply max pooling. And now you should do it yourself because you have enough information to do that. So how are you going to apply max pooling? C'est ça?
Yeah.
Is it like this one?
No.
It's fine if you don't have battery, you could use my computer to Yeah. Okay, so now you should apply the pooling operation. So how are you going to do that?
The pooling
I have already
operation.
defined
Yes,
pooling. Okay. Already defined pooling. The 2D pooling. Okay. And could you tell me what does the pooling perform? What is the operation that pooling does?
It is reducing everything into a 2x2
No,
matrix.
it is reducing right, but not into 2 by 2 matrix. It is reducing by a factor 2 by 2. So
Okay.
if you have an image of 28 by 28, it will reduce it to 14 by 14. And how it is done? How is it done?
By combining
So you take a 2 by 2
square.
and you take the maximum value. This is why it is called a max pooling.
Okay.
There's also an average pooling, which takes the 2 by 2 and takes the average of it. Do you understand what I have said? No?
Yeah.
For the other, you see what the max pooling does? An operation takes an image, for example, 2 by 2, 28 by 28, and takes squares of 2 by 2. And for every squares, it takes the maximum value. So for every 4 by 4, it takes one value. This is why at the end, you end up with half the image, 1/4 of the image you have, because you are reducing along the x dimension by 2 and the y dimension by 2. Okay, and then okay, so now we have applied this series of functions, and this is only one layer. So
we apply the other.
So we are going to apply it a second time because we have a mathematical guarantee that we should have at least 2 layers of neural networks to have a universal approximation. Okay, so we are going to apply. And actually, here I have defined conv1, conv2, conv3, but not pool1, pool2, pool3. Why?
Because they're the same operation.
Convolution is the same operation. I agree. Pooling, you should only have one because it's the same operation. But convolution, is it the same really the same operation? What is a convolution?
A convolution where we're passing like a filter on an image and applying a mathematical
so
operation.
we need a filter.
Yes.
And this filter will be learned during training. And actually, if you have put conv1 here and conv1 too, it says that you are going to use the same filter but this is not what we want. We want independent filters. So this is done in conv1. It's filter 1, w1. So actually, what's a convolution? A convolution could be rewritten as a matrix multiplication. So a convolution could perform this: x times w, with the times is the dot product, the matrix multiplication, plus a certain bias. Like for example, here in convolution, if you don't want a bias b, you should turn it off. So you do bias equals false, but here we are going to learn a bias. And the weights and the bias for each convolutional layers are associated with this convolutional layer. And for example, in conv2, it's another set of weights and biases. Okay, so this is why we need multiple convolution, but pooling has no parameters. Pooling is just pooling, it's just an operation. Okay, and now we are going to do it a third time. So go ahead and okay. Actually, I have put the comments here with spaces for you to write in between the spaces. So you could do that. Yeah, like this, because yeah, actually, if you are making a good code, you comment what you are doing. Sometimes when it's clear, like for example, for someone who has already done this, don't have to write the comments. The comments in Python are written with the hashtag, and then you write comments. Okay, so now we have applied convolutions, reuse, and pooling 3 times. And I have a question. And actually, I should have deleted that. But what is the dimension of X? You have the answer. I forgot to remove it. Yeah, we know that this is the output dimension, but why? What was the initial dimension?
It was 40 by 80
By?
by 1 by 128.
Okay, what is 128?
128 is the batch size.
Okay, it's the batch size. So there are multiple images, multiple spectrograms. And then you have 40 by 80. What is 40 by 80? Is the size of the spectrum.
Yeah.
Okay. And the end, we only have 128. We have 128 by 64 by 5 by 10. Why? Why do you look like this?
64, I don't know, but 5 and 10 are due to the pooling.
Okay. And why it is 5 and 10 and not 16 and 30? Why, for example, here? What was the starting dimension? Okay, and we said that the pooling was doing what? Yeah, it reduces the dimensionality in the x-axis by 2 and in the y-axis by 2. So actually, at the end of this line of the first pooling, what is the dimensionality? 20 by 40. And after the second pooling, it is, and after the third, 5 by 10. This is why we have 5 by 10. And why do we have 128 batch size still? Because we apply this operation for every batch element in the batch independently. And what is great with Python, it is parallelized over batches. So it does not cost a lot. It costs a lot, but it is less than doing that in a for loop, etc. So it is vectorized in a tensor. And then now we have the channel 64. Why we moved from 1 to channel 64? I will ask, for example, your colleague why we move to. Yeah, but you could try to give an answer. That's to do with how we define the convolution. The convolution, as I said, is a matrix multiplication. So if you take a matrix of size mn, you multiply it by the filter of size np, you end up with a matrix with size. You have mn multiplied by np, you have the result of size.
mn and p.
No, it's a matrix. No. Why np? mn, np. You end up with a matrix of size np. The inner dimension is reduced because we do multiplication and addition. So it is L and np. So here the m is in the first layer, it's 1. And then the n is number of channels n. And when you perform the matrix multiplication, you don't have any more 1 channel here. You have n channel at the end. So the n channel was defined here as 64. And this is why you have 64 here. And then here, this convolution is defined as 64 to 64. So it will go. So here, the dimensionality is already 128, 64 by 20 by 40. And at the second one here, the dimensionality is still 128 by 64 by 10 by 5, etc. Okay? Yeah, so this answers this question. And now we want to flatten. What is flattening? Flat. Sorry? Yeah, so flatten in the PyTorch language is just saying that we are not dealing with a tensor of size 128, 64, 5, and 10, and we want only a matrix of size 128 by the multiplication of all these elements. It's how do we say that? It's like a concatenation over the dimensions. So we don't want anymore 128 by 64 by 5 by 10. We want 128 by the multiplication of those dimensions. And this is done by a function of PyTorch called flatten. And I don't know how to write it, so I will just ask. So maybe ask for double T. So it exists in PyTorch, and you have a version. You could use it. So go ahead and do it in PyTorch. So as I said, in PyTorch there are the modules that are in Torch that's flattened, but you could so you could use it like this. You don't need to copy it. Just yeah, and Colab is helping you. And it's a function, but you need the parenthesis applied on x.
Yeah.
And you save the results in x. Okay, but actually, if you go back to the documentation, if you call flatten like this, it flattens all the inputs. So it will give you a single element. What we want, so we want something of size 128 by the rest. So we are going to use the start dimensions and the end dimensions. So the starting dimension is 0. We want to flatten from 64. What is the dimension 64? Is if you do that, start dim 0, it will start from 128.
Yes, so before is it just the second element?
Yeah.
Okay.
So it's
1.
Okay, so the dimensions are 0, 1, 2, 3. Yeah, and the end dim is -1. -1 means the last dim, and by default it is the 1. So by default it is -1.
Okay.
Did you understand what we did? I'm working on this computer because it's fine, but yeah. So here, what we want to do is to take this input of size 128, 64, 5, 10, and transform it, flatten it to 128 by this dimension, which is the multiplication of this dimension. If we do just a flatten, it will flatten everything. So it will give you something of size 128 times 64 times 5 times. We don't want that. What we want is to start the flattening from this dimension. So this is why we are going to use an option here. It is called start dim, that is available in the button, and say to PyTorch, okay, we want to start from 1 and not from 0. Do you understand what I just explained? So here you have to say that start dim is equal to 1. Okay, and now we have done this, but you don't know why are we going to do that. No one asked me, what are we going to flatten the tensor? What is the purpose? So since no one asked me, I ask you, why are we going to flatten the tensor?
It will make it easier to process.
But
the dimensions.
It's the same. It's the same number of elements. Actually, it's because we have not finished, so we need to apply those linear layers. our linear layers need a flattened dimension. It's matrix multiplication. So this is why we flatten to use FC1, fully connected 1, and fully connected 2. So go ahead. Now you can use fully connected. Which is okay, so I said I wanted to use fully connected and really. Each time.
Really.
No, the first time. Really. Great. And we don't need it in the last one. Because it's the readout layer, we don't use radio. Okay, and yeah, you have implemented your first convolutional model. Congrats. Okay, so let us run this cell. Will not show any error because we are not calling it. We are just defining the class. And now we are going to use it to make an actual training. But before, we need to define some other things, which are in the second. So here first, we are printing the model. And as you can see, so you have forgotten something here, miss. We said that we are going to apply convolutions, review, and pooling. This time, we applied pooling. Sorry, it's my bad. Pooling is not showing. Convolution, FCS. Okay, right. Sorry. Okay, and then we are going to define the actual optimizer, the scheduler, and the loss function. So the optimizer, we are going to use Adam optimizer. And yeah, so I said that the optimizers are stored with the package called optim. Yeah, and we imported it as optim. Let me check in the beginning. Yeah, optim. Okay, optim. Optim, and we want to use the Adam optimizer. So optim dot
Adam.
Adam, and I think there's capitalized K. And we wanted with learning rate 1e minus 3. What is 1e minus 3?
1 times 10 to the minus 3.
Okay, 0.001. Same as writing 1. I have noticed that you always forget the equal sign for variables. LR equal. Don't have time to okay. So let me just complete the other lines for you. Wait, DK. We need a scheduler, so we are going to use what was the one that we use? Let me just find the I'll just copy it for the sake of time. The scheduler adapts the learning rate. So it is done to adapt the learning rate. You can use a lot of schedulers, but then the most used nowadays are the cosine aligning annealing scheduler. So we're going to use this scheduler, and we are going to define a cross entropy loss function. The loss function calculates how different the labels are from the actual audio excerpts. So I invite you to copy this. It is on the practical work, so you just copy those lines. Copy them from But it is online. They intro to AI and then just searching the internet for intro to AI. It's the first website. This is the yeah. Before. Yeah. Okay, so once you have done this, you could run the wait TK is not I think the keyword in Adam, not WD, Adam. And the wait TK is called wait. You copy the whole cell and yeah, and missing, and you have to apply it on the model parameters, params. It does not know the model. The model is here. I think it does need only the model, not params of the model. So let's just check for the use case. Parameters, I guess, the keyword. Yeah, okay. So now you defined your optimizer, your scheduler, your loss function, you could launch the train. So here we are going to make the train. It's a for loop on the train loader, and each time it takes a batch and trains on that batch, it applies the model and you get it in output, and then you apply the loss function with respect to the actual ground truth, which is the target, and then you compute with this backward function, you compute the gradient propagation. So it computes the gradients for each parameter, and then the optimizer makes the gradient descent with the optimizer that step. Okay, and then you could launch a training, and you should wait a lot of time, but it will train, and you will see after one epoch it has 70% accuracy, and then after it, so you could complete this. Show me please just the optimizer complete the right steps. Okay, and yeah, so you need to copy also here. We need to mention the parameters. So model.parameter, write it for you. This. Adam needs the parameters of the model, and WD is called weight decay and not. Okay, so you can run the other cells. Did you manage to run? And yeah, you should wait for the training. And actually, what you will notice is that the loss function is getting reviewed at each step. Those are the steps you are going to perform. And yeah, at the end of the epoch. So what is an epoch? It's when your model has seen all the data at least once. So you take each time a random batch, but the second time you don't take the same batch, you take another one. So it's a partition. It's intersection is 0. You take the first batch, then the second batch, and when you have taken all the data, this is an epoch. And you could do many epochs. You could repeat this process, and each time the gradient descent will find the suitable weight up until one point when it will converge and you don't have much gain. So it might take a lot of time, as you can see. And to prove that your model is happening, that the loss function is reduced. The loss function is just the comparison between your output and the actual target. So if you have a loss function of 0, it means that the model is almost perfect, that it fits really the data. But this is not the goal in neural networks, because if you fix exactly the data, it means that you will not generalize to new data. What we want is that on the test set that is independent of the train set, we have a good accuracy. And this is why if a model is overfitting, meaning that it has 100% accuracy on the train set, it could behave poorly with the test set because those are new data. It does not see. Okay, so we could stop here. Sorry for 5 minutes at the beginning. I thought it was at 4 and not 2. Okay, and then I said in the notebook that you could run the other cell and see that the model actually predicts something meaningful. Yeah, you could do it on your laptop. And okay, thank you for your time. I don't know if you have a assignment or something do extra homework or no?
Yes, we have a final project where we have to choose one of the notebooks from one of the courses and make additions to it. There are different suggestions.
So maybe if you choose my notebook, you could implement a new model, for example, on raw signal data. Here we use spectrogram to adapt it on a new signal, raw signal data, or try to investigate new models or something like this. As you like. Thank you for your time and thank you for listening to me. And there is no one in Zoom, so your colleague has left. Bye bye. See you. Bye.